You can see on the screen the role of smart grid in facilitating integration of renewables. So 2 items here, smart grid and renewables. So let me talk about smart grid first, and then renewable, and then see how renewables can be helped to integrate with the grid, within the grid, using smart grid. Okay, now, smart grid, as an engineer, I have to define what smart grid is. Smart grid is not a done deal. It's a concept. You can achieve step by step, but there's nothing done. You can never say I'm done with smart grid. No, nothing is finished. So it's a concept with many elements where monitoring and control of each element in the chain of generation, transmission, distribution, and end use allow electricity to be delivered most efficiently. That's the thing, efficient delivery. That means you use the less resources to meet your load. So we talk about load side and supply side both. Now, when you talk about the grid, what is a grid? A grid is a network. This is the electric power grid, for example. We have natural gas grid, water supply grid, telecom grid, all of that. In our case, in the power area, the power grid, which is the picture here, is already quite smart. We have PMUs, fax devices, smart controls. It's fine. So what then is the issue? Issue is not the transmission network, it's more the distribution network where we need to pay attention to. Now, when I say this, people ask me this question, well, if that's the case, what is the motivation behind a smart grid? We want to make the grid smarter, safer, reliable, and more cost effective using advanced sensors, communication technologies, and distributed computing. Those are our tools in our hand: distributed computing, communication technologies, sensors. All of those can be used to make the grid smarter from the beginning to the end. That's the idea, beginning to the end. Now, what is the difference between a smart grid and a not so smart grid? I can explain that using this picture. Difference between, to me, a normal grid and a smart grid can be explained by the telephone analogy. On the left-hand side, you have the normal phone. The black phone has been there for, I don't know, 70, 80 years. Still, some people use it, audio only, no problem, you make the phone call. On the right-hand side, you have a smartphone. If I look at this black phone on the left-hand side, costs about $10, maybe $12, under $15, let's say. On the right-hand side is your smartphone, happens to be an iPhone. If you want to buy an iPhone today, cost you US $1,200. I got $15 and $1,200, 80 times more expensive. Phone is a phone, so it's a big deal. Well, yes, phone is a phone, you can make a phone call, but on a smartphone, you can do like we're doing now. You can do Zoom, you can do your email, you can do your social networking, you can do your clock, you can take pictures, you can do Instagram, all of that. Point is, if something gives you a lot of value, you are willing to spend money. So that's the issue. So smart grid is not cheap, but it gives you more things that you can do with smart grid that could not be done otherwise. That's why we say smart grid can be cost effective. It is not cheap. So just keep that thought in mind as we go forward. Okay. Now the question is, what is the starting point and the end point of this smart grid? Of course, power supply starts at the power station, fine. Then it has to be transmitted over long distance to make it useful at the load center. And when it reaches the load center, you have a distribution network where you have the step-down transformer, bring power to your neighborhood, to your building, your home, and ultimately to your refrigerator, your oven, your toaster, your microwave, whatever it is. So the point is, we have to look at the whole thing as a one space, one ecosystem, starting with the power station and ending at the generator. So I say Smart grid starts at the generator, ends at the refrigerator. Now then, what are the building blocks of the smart grid? At the top of the building block is the technology. Of course, you need technology to make it work, like sensors, communication technologies, all of those exist today, like smart meter, for example. They exist. No problem with that. Anytime you have many technologies serving the same end use, take example of a smart meter. It is manufactured by many companies, Europe, US, China, Japan, all of that. A power company should have the option to buy the smart meter, which meets their needs and can be supplied by multiple vendors. That means all those vendors must manufacture their smart grid using some standard which can be applied globally. That standards work for smart grid is ongoing. Most of it is done. So we don't worry too much about new standards for smart grid applications. It's almost there. Next is rates and regulations. Smart grid, smart meter, why would that be useful? For example, in the US, I'm sure UK, same case happens. In a hot summer afternoon, power gets very expensive. Why? Because many people are running air conditioners and many other things. Load is fairly high, very high load, peak load is very steep. At that time, it is costing the power company more to provide you that extra power. What is done in many cases to discourage high usage of electricity during peak hours, the price goes up. That's called time of use rates. That's a good example. But if we have to raise that, we mean power company has to raise the price, they have to let me know so that I can do something about it. That's the incentive for people to reduce their consumption and not spend more money than what they were ready to do. Those are rates and regulations which are still being worked on in the US, many other countries as well. So that is not done yet. So unless we have incentives to use electricity less or more because of pricing structure, we don't care. We say price is the same 24 hours a day, so how does it matter to me? That means to make the smart grid functional, useful, we have to have different rates. Fine. Finally, consumer awareness and education. I am a consumer, you are a consumer, we are power engineers, most of us, we understand these things. So we can be sensitive to the opportunities smart grid provides. My neighbor is a banker, or could be a lawyer. They don't know these details. So unless they are aware of this, they would not be sensitive and willing to participate in the pricing differential to reduce their load. So this is the biggest challenge today. The overall situation, the normal consumer, not most like us, have to be educated, made aware of these possibilities. That part we need to still work on going forward. Those are the building blocks of smart grid. Now, how has the grid evolved or evolving today? If you focus your attention to the top third of the picture here, before smart grid, standard practice, we all know this, power station, step up voltage transformer, transmission line, step down transformer, local substation, distribution feeder, circuits to your home. We have that going on for more than 100 years now. What is new after smart grid has been deployed or starting to deploy, we have rooftop solar, storage battery, the customer side storage battery, we have electric vehicle, wind turbines, many different things. Those are making life interesting for us because we have to be willing and able to absorb those sources like solar and wind, use battery properly, charge the electric vehicle when the demand is not very high. All that has to be coordinated. Smart grid provides the platform for that coordination between different supply sources as well as the demand has to be smart. So this is the difference. The dotted blue lines are the communication lines because you, the power company engineer, have to understand what's going on in your system so you can take action like changing voltage, changing the prices, and let the customer react. That's how the grid is evolving. Now, to me, the smart grid is a collection of many microgrids. In this picture, I'm showing you 1, 2, 3, 4 microgrids. Each of them has multiple loads like solar, rooftop solar on commercial and residential buildings. In the middle of the picture, with each of those boxes, I have a data network or access point, which will receive information from the power company, transfer that information to the homeowner or building owner so they can take some action to be more cost effective. Again, as I said in the beginning, smart grid helps us to be more cost effective because we can do many things. We have in the middle of the picture, the bigger one has a big building inside. On the outside, I have wind turbines. On the lower right-hand side, I have the bulk power plant, which is feeding the main power supply to the network. But each microgrid has some local generation in the form of rooftop solar. That's the setup. So this is how I see things evolving over time. Now, to make all that come together, fit together, we have to merge power flow, which is happening, with information flow. How does it work? Well, we have to integrate communications and power flow. If you look at this picture, this is the power infrastructure, meaning what we have been doing for 100 years now. Power station, step-up transformer, transmission line, your neighborhood substation, step-down transformer, feeder supply, homes, factories, buildings, all of that going on. You can have some local fuel cell generation, flywheel, battery storage, all of that can be part of our system. It is part of our system. Now, what is new, we are now superimposing that electric power infrastructure with information infrastructure. That's a communication network. You'll notice in this communication network, all the red lines have arrows pointing in both directions, up and down or left and right. Why is that? We have to provide two-way communication for smart grid. Example, I have smart meter at my home here in Virginia, in the US. It is receiving information from the power company and how much current has been delivered, power to my home the last 10 minutes, last 1 hour, fine. At the same time, my smart meter sending information back to the substation, giving my voltage profile and frequency. I can see that online in my case. What is the voltage now, frequency now? That's the two-way communication example. How does this work? The way it is set up in terms of communication, for my case, my smart meter is transmitting information in real time using microwave mesh structure. So microwave is sending data back to what is called a data concentrator. So the microwave mesh structure is provided by the power company to collect information from my smart meter for them to see. Fine. Once it goes to the data concentrator, it is then transmitted to the substation using mobile phone GPRS network. The power company is renting bandwidth from the telecom companies to receive data from the data concentrator into substation. From the substation, power company has their own fiber optic network, physical network, substation to the control center. That's how the voltage information from my house is going to the control center and they can take action. So that part is new and it's happening. If you have a smart meter, there has to be some communication, like I just said, to make it work. Good, we can come back to that if you have questions later on. Now, this is a smart grid part. Now let's talk about the supply side. We have rooftop solar. In Japan example, UK has similar things. Offshore wind, UK big on offshore wind, electric vehicles, all of those are changing our life because we have to receive these new supply sources and make them work to the best of our capacity. Fine. What are the issues? Wind and solar are free, but they're intermittent. They're not guaranteed all the time. Number one. Hydro is space limited because you cannot put hydro plant in Manchester or in London, not in New York City, but it is available for free when it is allowed in a given space. So resource is free, but not always usable. That's the challenge, and see how smart grid can help. Okay, let's focus on wind energy first. This is data from northwestern US, Bonneville Power Administration, their data. I'm showing you data for 4 seasons: winter, spring, summer, autumn. Winter load in the US, very typical, 2 peaks, one in the morning, 7 o'clock or so, one evening about 7 p.m., typical load shape in the US. In January, this is average data for the month of January, the wind output peaks about midday and then low in early morning and low at night as well. Not a good match between supply and demand. Let's look at springtime. Again, double peak for northwestern US. The wind is pretty strong early morning hours, slows down by midday or 5 o'clock, 6 o'clock, it is very low. When the peak begins, the second peak begins to happen, wind output is very, very low. That's spring. Let's say summertime, very different. Summertime in the US, the load shape is very flat, very wide peak from about 1, 2 o'clock to about 7, 8 p.m. That's the blue line. The red line is your wind output. Wind is low in the morning, gets very low by midday and early afternoon, and it picks up at night when the load is slowing down, going down. Summertime. In the autumn, again, 2 peaks are back. Wind is very high in the early morning hours till midday or afternoon, then goes down. The second peak happening about 7 p.m. wind output is very low. Point I'm trying to make is, in this example, the supply side and the demand side do not match. We'll see what you can do about that. More examples. This is data from Texas, 150 megawatt wind farm. Is going fine in the early morning hours, about 5 o'clock or 6 o'clock. It drops by 30%, 140 goes to less than 100 and stays at that level, goes down further. By late evening, it picks up. That's life. Question how you deal with that. More example here, even steeper drop in 10 minutes, it went from 140 to maybe 50 megawatts, then picks up. So this is life, how we deal with it. More examples. Again in Texas, January 1st, 2008, we have showing you 2 days back to back, 01 and 02 January. It's a 4,541 megawatt wind farm. Early morning hours on January 1st, I'm getting about 2,200 megawatt, slowly going down, goes to about 50 megawatt or 100 megawatt by 11 o'clock, then stays low for the rest of the day. Next day, 2nd January, under 500 most of the day, then picks up. You can say, well, this is a problem we know. We can buy a lot of batteries, fill this gap. You can. Batteries are very expensive, number one. Number two, next day, wind is fine, next 2 days. If you had a lot of batteries to serve day 1, day 2, they're not being used for day 2 and day 3 and day 4. What does it mean? You've invested a lot of money, but that money is not being used to give you returns because not being used on day 3rd and 4th of January. That's why we are talking about how to play with the demand side so that we can have some help and not to buy very, very large batteries. Okay, now that was wind part. Let's talk about solar. This is my building at Virginia Tech where I work. I put rooftop solar to see how the solar output matches or doesn't match the building demand. Okay, this is rooftop solar. This is same rooftop solar, sunny day, but winter time. So here I get full output. Here, sunny day, but no output because my panel is snow covered. We don't go to the roof and clear the snow, never do that. So we just say, okay, just it's not there, it's not there. The point I'm trying to make is if you are depending on solar to some extent, when it snows, you have to have some other alternatives to make your building function. Now, some data from the same system. I picked up a nice clean week. You can see it's producing about 5,500 watt, or it's a 6.4 kilowatt system, not very big. I'm getting pretty close to peak almost every day, except the fourth day was a little bit low. That's fine. If this is what you get most of the time, you're in good shape, but you don't. Another week, same system, output is 40%, 30%, 60% like this. So what do? Challenge, not solution yet. Let's look at the day. One day, typical sunny day with some cloud movement. Cloud movement means you got fluctuations in output. So how you deal with it? If this is the picture you are dealing with on a regular basis, you can say I'll use some battery to catch these low supply periods. You can do that. That's a good day. This is a bad day. Meaning you don't get full output at all, a lot of supply side fluctuations. That's my challenge. Okay, now solution options are the following. Battery we talked about, no problem. These are now big batteries, 2 megawatt, 4 megawatt hour batteries being deployed in many places, including US. Second one on the lower left is a pumped hydro storage plant. Battery can give you almost instantaneous response, charge or discharge. The pumped storage hydro plant, what is pumped storage hydro? During off-peak hours, you'll pump water from the lower reservoir to a hilltop and hold it there, pumping. Then during peak hour of the day, you let the water come down from the upper hill reservoir to the dam and turn the generator in the process. And then the upper reservoir depletes, and after some time, you don't have much left, and you are now done. Peak hour is over, so you can start again after midnight. When the demand is low, pump it back again. That is called pumped storage hydro plant. You can imagine it's a mechanical system. When the water coming down, I've been to this plant in Virginia. The pipe called penstock, the pipe diameter brings water back from top to the bottom with 12 feet. Two of me standing on top of each other, the diameter of pipe. You cannot flip it in a matter of minutes. It has to be done for multiple hours at a time. The point I'm trying to make is hydro pump storage is a good thing, but not enough to deal with this kind of situation. Cannot do that. So that's pumped storage hydro. The lower right-hand side is my compressed air storage project. There's some pilot plants being built all over the world. Germany has some, I know US is building some. But what happens there, during off-peak hours, you use electricity to compress air and dump it into a sealed space. Could be a salt mine, could be some mine which is sealed, doesn't leak any air out of it. And hold it there. During peak hours, you release the compressed air to supply a gas turbine. As you know, a gas turbine requires compressed air for firing. So you're not compressing air at 4 p.m. on a hot summer day, the compressed air coming from the ground up. That's possible. Again, that is not easily flippable. You cannot go from compression to generation right away. So only battery can do that for you. Fine. Something else I'll talk can also do that for you, the short-term variations. Okay, now let's go forward. Hold on a second. So this is my other solution. I talked about supply side, battery, pump storage, hydro, compressed air. My challenge is to deal with this situation. That's my challenge. So I can deal with this, not very well always. Now I'm talking about how I can play with the demand now, not the supply, to match this fluctuating supply from the solar, like you saw. Let me focus on the bottom part of the screen first. Demand side management. This is going on for at least 30 years that I know of. Power company will turn off your electric water heater when the peak is going to be high, or turn off your air conditioner so that they can save some electricity on a hot summer day. That's going on for many years. The problem is with the hot water is not that difficult because you have a 200-liter tank. If this turn the power off, you still have some hot water to use to take a shower. It's okay, but not many people taking shower back to back. That's one. Air conditioning, what they do, if you agree with the power company that you will let them control your air conditioner, turn them off, that's what I mean by control, on a hot summer day, they'll give you some money. Not very popular because people don't want to be hot on a hot summer day with their AC not running. So what is the option? We call it demand response. Demand response is a customer action. Now the power company is not turning anything off. Customer takes care of it to meet a certain target. Why did the power company turn my AC off? Because they wanted to save 5 kilowatts, that's the load, from my air conditioner, 5 kilowatts. What I'm saying, don't turn my AC off, give me a target. You, power company, telling the customer, give me 5 kilowatt savings so I can deal with the peak challenge the power company is facing, 5 kilowatts. I see that number as a homeowner, and I have many options: air conditioner, electric water heater, clothes dryer, electric oven, and electric vehicle. I can then play in my situation and decide what of those 5 loads, each is 5 kW or more, which one I turn off and how long. I will not turn off the AC for 2 hours straight and give the power company 5 kilowatts. I'll play with the AC some. I would not turn the clothes dryer on. I may not heat my water. I will delay baking my cake. I would not charge electric vehicle. All of that is my decision. That's demand response. Yes.
Can you put your PowerPoint back?
It's there. You don't see it?
Oh, probably we can't see your screen. Probably you need to quit your screen and reshare your screen. We can only see you, not your screen.
It's interesting. Okay, let me do this. Hold on.
Thank you very much.
This is interesting. Can you see it now?
Yes, it's back now. Thank you.
So you did not see the screen, demand response screen, did not see? Okay. I'm glad. If this happens next time, please let me know right away. So this is the demand response, which is customer decides how long, which appliance to be turned off. Fine. So now we have a situation where I call it the new paradigm, meaning historically we call demand-driven supply. Demand is the independent variable, meaning the power company will make load forecast 1 year, 5 year, 10 year like this. They make a load forecast. And based on that forecast, they build power stations to meet the demand as load grows. That's going on for many, many years. New reality is, I call it supply-driven demand. Now, my supply is the independent variable. Solar, wind you saw before, independent. So what do I do to match the fluctuating supply? That's what I'm saying here. Demand needs to adjust to meet fluctuating supply with help from storage. If you do a brute force solution, brute force meaning I don't care how the supply changes, I have enough battery backed up, I don't care. The whole thing can go to zero, the solar battery will take over. It's possible, but very expensive. And you wouldn't have enough space to put that in anyway. So what I'm saying, I want to play with the demand somewhat, therefore reducing the size of storage I need to meet my demand with available supply. That is what I call smart grid ecosystem. So look at this picture here, next slide. This is, to me, a smart grid ecosystem. Smart grid to me starts at a smart building, because that is the end point of the power supply. Could be office building, could be a factory, could be home, shopping center, whatever it is, smart building. So this has to have intelligent building automation system, which will, like example I gave you before, I was told by the power company, cut my load by 5 kilowatts. I have intelligent system, looks at number 5 kW, looks at what I'm doing now, electric vehicle, air conditioner, water heater, clothes dryer, and oven, all of that, and makes a decision what to be done when. That's one. Second is a master smart devices, meaning my oven should have an IP address so I can check its status and make decisions. That makes me and my family, my wife, very productive. We are not suffering in a hot summer day. We are still baking our cake, drying our clothes, but not creating problem for the power company by creating extra demand for them. That's how I will be part of the grid integration network. So this is building automation system, smart devices, sensors, users are productive, and I am part of the grid, integrated grid. Smart building. Now you go to your campus, Strathclyde and Manchester and all that, you have many buildings on one campus. So you can play with different building applications, different building usage. For example, on a campus environment, 4 o'clock in the afternoon, one building, which is mainly classroom, classes are almost over. So it's less occupied. Next building could be a conference center, a conference going on. So they need a lot of air conditioning. So can you then, in this case, turn down the air conditioner in the classroom building in real time and save that power or electricity for the next building, which has a conference going on? If we did that, the power company would not see any difference. Even the one building, conference building, calling for more power, but the classroom building is calling for less power. Some of the two is the same as before. That's smart campus. A smart city can have many such smart campuses, including large shopping centers, corporate research centers, hospital network, universities, all that. And then all of those will belong in a smart grid, which allows bi-directional flow of energy, remote control automation, and integrating these fluctuating solar, wind, all that. This is the big ecosystem I'm working on. Now, what is the smart building? Just as an example, a building has heating, ventilation, air conditioning, lighting, water supply, sensor networks, security camera, fire emergency, and many other things. All of those have to work together. For example, if one part of the building is not being used, why keep the light on full capacity? You can dim the light somehow so that your light load will be down. Similarly, if you can afford to change the temperature setting in your thermostat, save energy. All of that makes a building smart. Then I just spoke about this already. I can have many smart buildings. They can be interacting with each other so that large supplies of solar fluctuation can be absorbed. At Virginia Tech, we have a large parking garage, rooftop solar. When the rooftop solar is fluctuating because I depend on that solar for my building, academic building operation, I can go there, remotely control some hallway lighting, corridor lighting, classroom lighting, change of the thermostat setting, and manage that. If I did that, I still not need some storage, but not as much as if I did not play with the load, as I just said. But for that to happen, you have to invest for monitoring and control of these loads and lighting circuit, all that. Just make sure it's not free. You have to invest somewhere as well. Okay, now, so this is what we are talking about now, summarizing. Smart versus not too smart, not so smart load control. What do you mean by not so smart load control? That's my example of power company turning off my air conditioner. That's not so smart because I'm suffering. Smart control is what I just said. I would take the number from them, what they want me to save, and decide between my 5 loads, EVs, AC and all that, what to control. That's one. If I can do that, then I can downsize my storage because the net effect between supply and demand, the delta, is shorter than the delta if I left the demand as it is and supply was low. So that's how storage will be less. And of course, I can have smart inverters for PV units, which can control the voltage, control the power P and Q, and make it more friendly operation. Fine. So done. Technical part is done. Just one more slide. Why I do all this work. Have been a volunteer for IEEE for more than 40 years now. And I noticed this. We all are suffering from COVID-19 and all this problem. But we know we'll get out of this. But when we get out, we'll have a new normal. It will not be the same as 2019. It'll be different. Then how we deal with it, like we are doing today. I'm not in UK giving a lecture. You have taken the time off this afternoon to listen to me. So this is, to me, a collaboration and cooperation so that we can benefit each other. This is going to happen more and more as we come out of COVID-19 pandemic. So we need a community spirit. I hope I can be a partner or a party to this activity. For this to happen, we have to make IEEE broader. IEEE has engineers, physicists, some physicians, doctors. We have to bring IEEE to the society to see how IEEE can help this remote conferencing, teaching people how to be more energy efficient, how to use a smart building concept to save energy. All of that we have to be participating in. So, but for that to happen, we need more participation from volunteers globally, not just North America, in IEEE governance, meaning IEEE committees, IEEE vice presidents, IEEE president should be more global in their outlook and come from many countries. So that would be my goal. And finally, this is very true. I've noticed that in regions 8, which is your part of the world, Europe, North, Middle East, and Africa, the number of senior members and fellows in region 8 is less than regions 1 through 6, for example. One reason is awareness. It's not difficult to become a senior member. If you have 10 years of experience, you got a PhD, you've got 7 years already done, so 3 more years. Most of you have that. But you don't take the time to apply because you think, well, if I apply, it takes time, I wouldn't get it, so what's the point? I would put some, I guess, system in place to encourage through the chapters like UKRI chapter sections. So people who are qualified will be encouraged to apply. You can apply online yourself. You need 3 references. When you do the platform for you, we'll make sure that enough volunteers are willing to be references for you. That's one. Second part is IEEE fellows. Again, the same issue. Number is small in regions 8, 9, and 10. You're region 8. I have in PS set up a committee which encourages and reviews applications for fellows and make them better. That happens. So this is it. As when said, I'm running for IEEE president this year. I was PS president. I was in the IEEE governing board. I've set up the PS University corporate engagement program. I set up the chapter council to make the volunteers at the local level more powerful, more industry activities. They have budget now to travel within the country, like Africa, for example, that our region 8 rep has set up, helped set up. So that's going on. Finally, my website is here, srahman.org. I have already posted this slide deck on my website. You can go there now and look at it, download it, no problem. So I'll stop here and then take questions, if any.
Okay, thank you very much, Professor Safar Rahman. It's a very great and inspirational talk and a very great leader for IEEEs. So thank you very much. And now, this seminar is organized jointly by the 2 chapters in the UKRI, Industry Electronics Society, which I represent, and also Power and Energy Society, and my colleague represent panel duties. Are you ready to take on the questions? So if you want to raise any question, you can either to speak out in turn, or you can type your question in the message chat and we can ask on your behalf. So,
I can see many people here, Xiaoping, Ahmed
yes, your
Zola.
friends sending greeting messages. Kanli and Ahmed, they know you very well.
Right.
Yeah.
Okay, your turn now.
No, it's thank you so much, Safur, for your presentation. But I am one of the people who has opinions that human being, once they involve in anything, it may be a crisis. Yeah, this is my point of view, and sorry for that. I am human being, but because one of the things which I don't agree on, that one day, yes, we have people agree on the smart grids and they will follow the rules, but there are people not, because not all will agree that the utility will ask you now, please turn off your washing machine, and you will accept this. Or if he will need you to turn it at 2 in the morning just for demand side management and all load shifting, all of this stuff. So do you think that we can reach 100% smart grid in the future? It's a very green land of research. I am working on it. I have books published on it, but till now I see that we can be smarter, but not smart. So
Okay, Ahmed, thank you very much. Let me address your concern. You're very correct. Let me give you a story first before I answer your question. My story will help you to understand what I'm saying. I used to go to Cairo very often. I'm in Cairo now, a few years back. The hotel is fine. I'm in friend's home, light goes off. That happens frequently. Why? Because in Cairo, people come from work about 6 o'clock, they start cooking, watching TV, taking shower, all of that happens at the same time. So the demand shoots up. The feeder that is feeding these homes unable to deal with that. So what they do scheduled or sequential blackout, meaning they turn one feeder off for some time, then bring it back, next feeder on, fine. That's how they manage it. Then the people said, well, why me in my house has no air conditioner? Why am I suffering? Because biggest reason for the load spike is air conditioning. So power company said, fine, when we reach a crisis point, we'll send a SMS to you, every house, please turn the AC off. If you turn the AC off, you're not going to die, right? You'll be okay, but you will let power come, everybody is satisfied. As you said, Ahmed, just now, not everybody listens to people. So what they did, when we, power company, send the SMS to you, if you do not turn the AC off in 5 minutes, I'll turn the whole house off. So you have a choice now.
yeah,
Don't listen to them, our house is off. Then people listen. That's one extreme example. Now coming back to your number, as I said in the beginning, we will never reach 100% smart grid because people will not listen. Even if you give pricing differential, some people say, oh, I have enough money, I'm rich, I don't care. This happens. So this is the thing we have to deal with. So as I said, my answer is not 100%, but we do the best we can. I'm seeing more questions on the screen. One from person named Hiramoni Khatun. May I know what is the highest efficiency solar panel you have used? I have used today about 20% panel efficiency. That's pretty good. But on the market, there are high efficiency panels. But as an engineer, I have to be cost conscious. I can get high efficiency panel, but pay much more. But 20% number is pretty normal right now. So that's one question. If I can go on, when the next question, do you see the role of UK National Grid Transmission System Operator reducing in terms of making generation match demand, if instead demand is going to match generation more in a distributed way, or there'll still be a significant role for national coordination of generation and demand? Very good question. I had a PhD student did his research on this topic, this very topic. So what we do, the demand and supply is matched at the system level, like you said, TSO level. How does it get translated to my home? The way we set the problem up ourselves, we said the power company knows, looking at the forecast, from 1 to 5 p.m. today, they'll be short by, you pick a number, 1,000 megawatts, but a system of 20,000 megawatts, in my case, in Virginia. 20,000 megawatt system, 1,000 megawatts short. How would they distribute the 1,000 megawatt cut in their system? They have 100 substations in this company. So 1,000 megawatt, 100 substations, 10 megawatts each substation. They will then decide which feeder to cut how much and make a decision. And then based on that information, I'll get a number for my house. I need to cut 5 kilowatts. That's how it is distributed. So you're right. Starts at the top, numbers come down to the individual home. That's how we have publication on this topic. If you like, send me an email. I'll send you the paper. So this is the one from Kang Lee. Broader global collaboration, leadership, engage community promoting facility landscape, and UK net zero 2050. Those are targets. I like targets, but I like roadmap more than targets. I want to see what UK will do in 2025, 2030, 2035, 40, and so on. Then I know I can believe that number. Otherwise, target is a target. So it's a good, I guess it's a good target, but it will need some work. So when I don't see any more questions on the chat box, but somebody can speak up, please do.
Yes,
Yes,
please.
Cypher, yeah, may I?
Please, please.
Yeah, Cypher, I think you give a very nice talk. In addition, I want to mention in the past, the IEEE, yes, under your leadership, you have done a lot of important work. For instance, I remember in 2010, under your leadership, IEEE launched 2 very important transaction. One is a transaction on sustainable energy, another one transaction on smart grid.
Right.
Actually, both transactions play increasing important role. In the meantime, also during the period, some global smart grid conference series created. That's
right.
one. Now, probably, my understanding is the smart grid development comes to a very important stage. So my question is, the smart grid development probably right now is different from that 10 years ago. So in your point of view, how actually the IEEE, even IEEE as a whole, can help with the society and a community to develop smart grid technology further?
Okay, good question. As you know, we PES have an annual conference on smart grid, ISGT. It held in Manchester, I think 4 years ago, roughly. We do one in the US, one in Europe, or Europe, mainly Europe, and one Asia, one Middle East. So I started that in 2010 in the US, 10 years ago now, the ISGT conference. Objective was to bring awareness among the players, players, not only us, regulators, policymakers, government people, academics, of course, industry people. So we bring, when I do the Smart Grid conference in Washington, I've done it many times in Washington, I bring in policymakers, politicians, regulators, industry people, all of that. The reason is very simple. As I said in my pyramid example, unless multiple stakeholders do not see the benefit, like Ahmad said, some people do not listen to what you said, that's fact, but we want most people to listen to us. That's the challenge. So you're right, if you want to make the smart grid a reality, it's not technology, it's people accepting the technology and willing to behave. For example, people have accepted Zoom like we are doing now to talk. 6 months ago, people didn't know what Zoom was. I used Zoom for 2-3 years. That's a different story. So that's what I said in my last slide. Our objective will be, as a citizen of a given country, we are engineers, fine, but we also social participants. So I would focus on that part through your children's school, your colleagues at work, other engineers who are not part of IEEE. Have a lunchtime discussion in your company or in your department. When bring in people from communication group, electronics, people from electromagnetics, people from computers, and so on. So this would be my message.
Yeah, thank you very much.
One question here, I can see it now. How do you see the roadmap for energy storage in the next 20 years for smart grid development and low carbon economy? Very good question. I'll answer that with an example. I was visiting Hawaii a few months back. Hawaii has very sunny weather, very good solar opportunity, and very expensive electricity. Why expensive? Hawaii has no nuclear, no coal, no gas, only oil-fired generation. Very expensive, about 2.5 times US average. So because it is sunny, the government there has given a lot of incentives for solar. So many homes in Honolulu have rooftop solar, maybe 60-70%. So during daytime, they're producing more solar-based electricity than they can use. That's one. So house is self-sufficient, but nighttime, no sun. So they have to depend on the power company. Power company has the connection from the power station to the home for a long time. Now, because of solar, power company is selling less electricity to the house. Revenue has gone down by a factor of 2 or 3. Power company says, I have to maintain my transmission line, distribution line, substation, transformers, switchgear. My cost has not gone down, so my revenue has gone down. What do I do? So for the situation there, the power company is charging the home a connection fee. If you want us to supply power to you on a cloudy day or at night, you pay for energy that you buy, kilowatt hour, plus some extra fee on top of that. That makes the house economically difficult to manage. So what are they doing? They're buying batteries. That's your question. They're buying batteries so that at night, you don't need the power company anymore. They're going totally off-grid. In Hawaii's case, it makes sense because cost of electricity is very high from power company, very sunny place, and battery price has come down, plus big incentive from the government to go solar. In fact, in Hawaii's case, they get their money back with the incentive in less than 3 years. Less than 3 years. Makes sense. So my answer to this question about next 20 years, as the price of storage comes down, price of electricity goes up, you'll see more and more people, if they don't go fully off-grid, they will be buying less and less electricity. So that's the answer to this question about next 20 years. Now, other things can happen. Like I gave a talk in Chile yesterday. Chile has a lot of solar power, excess power. They're considering using solar energy to make hydrogen. That's a storage. Store the hydrogen, use in a fuel cell, or use in hydrogen combustion for IC engines. So those are things. Those things I will say as examples for the case you are talking about. Okay. Any other comments? Let me see. I don't see any other comments on the chat box. Yes.
Here's a question here on another chat window. Dr. Zhou Beitian from Birmingham University. The question is, thank you for your presentation. How do you see the transport electrification and transport integration with the renewable in smart grid? Does the transport only play a role for future smart grid? Is there any opportunity in transport renewable energy integration?
Very good question. The electric vehicle is a good example. Today, if I buy a Tesla car, it's about 40 kilowatt battery, 40 kilowatt. My house total load is no more than 20 kilowatts. If I put that charging load for my house to my distribution network, overnight, it looked like 2 more buildings have come on my street. So that's why if you buy a Tesla, I'm let the power company know I bought it, and they will check the transformer capacity and tell me whether this is possible or not. So that's how it will go. My point is, this is a good thing because electricity demand will go up and we'll be using less fuel, less CO2. The issue is infrastructure improvement. This is an expensive thing. So we cannot just say we'll promote more and more EV. We have to invest in infrastructure improvement. In the Virginia now, there's a program for school bus electrification. They'll put school buses electric. The biggest challenge is those buses about each have 60 kilowatt load. So 60 kilowatt, 4 buses are about quarter megawatt load. They have to upgrade the substation. So answer is not very simple. You have to look at the infrastructure investment to make it happen. So the reason I'm saying this would be a slow process because of the investment needed. It'll happen, but it'll be a slow process. Thank you.
Thank you very much. Any other questions? Professor Xiaoping Zhang, do you want to raise any questions?
Yes, I think Cypher have a lot of interesting is Cypher at the moment also some research work going on as well. I think probably you have heard about the Stanford University. They have been working on so-called 100% renewable energy vision. So do you have any sort of suggestions about 100% energy generation from renewables? What's the key barriers to achieve that?
That's a good question. Renewables include hydro, solar, wind. UK has 2050 target of net zero emission. That doesn't mean all renewable. China has a target by 2030. 52% of all of China's electricity will come from renewables. 52%. That's happening. 2 issues here about technical feasibility. One, you probably know, issue of inertia in a system so that stability can be maintained. Inertia today comes from large generators, hydro mainly, thermal, and so on. If you go all the way to inverter-based systems like solar and DC, then there's no inertia. So can we provide inertia from electronic devices? You see that debate going on today, and it goes both ways. I believe it can be done, but it'll take time. Other thing is cost. The power plant being built today, coal, nuclear, hydro to some extent, 50-year life. You would not retire them till toward the end because of the stranded cost. So that will reduce how quickly the renewables can penetrate the market. It's happening in China today, but China has problem because a lot of wind is being left out, not being used because its system is full. So it is not a technology issue only. Technology penetrates if you create the proper environment. And technically it's feasible, but it is not going to happen by itself. Zoom existed for 3 years. I've used Zoom for 3 years now. It is not used. We're forced to use it, and we're using it. Similarly, if for some reason we lose all the coal overnight, then coal plants are idle, then you go for solar. One more example. I was in Japan after Fukushima happened in 2011. They have nuclear all shut down. A lot of supply shortage. So what they did, they were using at the time a lot of efficient devices. Drop your load, efficient lighting, less air conditioning, less fan load, and the wind and solar picked up. So there are other forces which can make technology move faster than we normally see.
So can I ask you a question regarding CO2 emissions? So I asked expert in the past, but I'd like to have your opinion on the near zero future things, really. If we achieve zero emissions in about 30 years' time, is our existing plantation will be starving out of food? Our CO2s really the ingredients and the food for the existing plantation. Is this target too radical or not?
No, net zero emission doesn't mean net CO2. Net zero means you produce some CO2, you absorb some CO2. That's the net zero. And that
absorbed
you're right.
by the plantation.
Exactly.
How do you measure that? We can control the release part of the CO2. How do we measure the absorbing part?
Well, we do not measure it. We go back to few thousand years ago, or at least 500 years ago, when we did not release CO2. We had no coal plant, no gasoline, no cars, no power plants. What happened? So there is some natural CO2 production, which is done. Oceans emit CO2 as well, because carbon is stored, and they are balancing each other. So we knew that before we added CO2 to the atmosphere ourselves, the world existed. People lived 300 years ago. Europe had a lot of people running around. So we don't have numbers to measure, but we know there was a equilibrium. We'll bring it back. So we want to go to that level, equilibrium, not zero CO2 production.
Yes, but the increase in the CO2 has taken over 150 or 200 years, arriving this point. But we are cut CO2 or reduce CO2 rapidly just over 20, 30 years. I mean, the existing ecosystem, is that adaptive enough to take on such a change? I have no idea. I'm not an expert in that field.
No, very good question. Let me give it a thought for a second. If you go back to pre-industrial days, like 1850 or before, yes. You said 150 years, you're right. We had no man-made CO2. CO2 always happens. We call anthropogenic, man-made CO2. There's a difference. That was zero. So ppm for CO2 was 250, 300 at the time. Now it is 450 today. If it goes over 700 or 650, we have problems. So the extra CO2 we are producing today is not absorbed by the trees. They're going up in the sky and staying there. That's how we see the greenhouse effect. We want to stop that part. So if you want to bring CO2 parts per million in the atmosphere below 400 or so, then trees will get enough CO2, but we would not add to the global warming and greenhouse effect problem.
Thank you very much. Do we have any further questions? Yes, please see the message part, the chat.
I get two questions here. Do you see the future of sufficient renewable power to cover all energy requirement of mankind? If not, why? If so, what is the likely roadmap? I just answered that partly, and I'll repeat myself here quickly. On paper, in theory, it is possible to meet our energy requirement from renewables. Answer is yes, but it will take time. And hydro is pretty much developed globally. Some left in Africa, China a little bit, India pretty much full, North America pretty much full. So what I'll see, there are more biomass application for power production. That's how I'll see this happening, number one. Next question, large scale use of new energy technology is still a problem. In your opinion, is the development of energy storage technology still the key to solving energy supply? I think so, maybe 80%, but I am also focusing on the demand side. You can manage your requirement using less energy. For example, if you move from incandescent light bulb to LED light bulbs, you save 80% of electricity demand, number one. You can get high efficiency air conditioners, reduce your demand. You can get variable speed motors for air conditioners. You can insulate your homes better, so less leakage happens. So all those things have to work together. It's not just more supply, more supply. We have to focus on the demand side as well. That's what my talk was this morning. Demand side is a big player. So that's my roadmap. Thank you. Any other questions?
One more in the chat.
Yeah. Okay, I don't see that. Can you read that to me when?
Large-scale use of new energy technology is still a problem. In your opinion, is the development of energy storage technology still the key to solving energy supply?
Very, very good, very good. Large-scale development of storage would be a big contributor to this. Storage doesn't mean just storing in a battery. It could be pump storage, could be compressed air energy storage, could be storage in other ways we don't know yet, like thermal storage, ice storage. Many storage technologies will play a role in solving energy supply. The question is the following: are these technologies mature enough, economic enough, and well known enough so that you can consider that as a component in your building power supply? For example, building is a building. It has air conditioning, heating, lighting loads. You can supply that using power companies' grid power. In addition to that, you can put rooftop solar. You can put some battery storage. You can put thermal storage. And you can use efficient appliances, equipment to make your demand low. So it has to be a mix of all of those things, not just supply and storage.
Thank you very much. Do we have any further questions, please? Panagiotis, would you like to say something about the second seminar from Professor?
Yes, thank you, Wen, and thank you, Professor Rahman. That was really interesting talk. Yeah, we have an upcoming seminar on the 29th on a different topic. I'd like to just thank Professor Rahman one more time for taking the time to give this talk on behalf of the PES UKRI chapter as well. So thank you.
Thank you, all of you. Good questions. That tells me you listened to what I said carefully and formulated these good questions. Thank you very much. Enjoyed it. Keep up the good work, and I'll see you again, some of you, on July 29. Thank you very much, both Wen and Panagiotis.
Thank you very much. Before you go, I would like to point out 3 things. Firstly, please vote for IEEE president and to choose the best leaders you think which should lead the whole IEEE to the right way forward. Secondly, I have recorded this seminar. I'll discuss with the professor on the sensitive information. It is possible we can remove some information, make the video available either on YouTube or on IEEE section website. If you cannot find the information, please go back to me for the video of this webinar. And thirdly, we got follow-up sessions. Please follow us as well. Thank you very much for everyone.
Okay, bye-bye.
Okay, then bye-bye then.
Bye-bye.
Thank you. Bye.
Thank you very much.